Hi everyone. So I'm going to start with a review. We started chapter 9 last time, and the first topic that we covered is center of mass. And for the center of mass, there are several equations we developed, and I want to talk about in one dimension first. So let's say we have an x-axis, and here is the origin. So this is x equal to 0. And let's say we have several masses, let's say m1, m2, M3. So this is how we started, but this is not very realistic. You cannot like have some beads on a massless rod or something, right? But again, this is just to understand the topic. That's how we started. And we're saying then M1 is at a distance of x1, M2 is x2, and M3 is x3. So these are really the position vectors, okay? So you need to measure them from the origin. So that's really important for these type of problems. Make sure you see where the origin is, okay? And so because that's the relative distance is measured from the origin, because those are position vectors again. And then what we said is if we have like three masses like that, we said we can find the center of mass of this system. So the system is made of these three masses. Since this is one dimension, we know that it should be between, the center of mass should be between M1 and M3, right? If M3 is much bigger compared to the other two, it's going to be, center of mass is going to be closer to M3. Or if they are all the same, and also the distance between M1 and M2 and M2 and M3 are the same, then the center of mass of the system would be right at M2. Okay, so but it would be in between 1 and 3 if that was just like this problem, if it was a one-dimensional case. And so the topic is very intuitive, but in 3 dimension things may get a little bit more complicated. Sometimes we may not find it without solving correctly. So we need to understand how to solve things, okay? So we use x center of mass as, for this case, we said we would multiply m1 with its position x1, and then m2 with x2, and then m3 with x3, right? And then we divide by the total mass. Total mass is capital M. What is that? M1 plus M2 plus M3, right? So in this chapter, if you see capital M in the workbook, that means it's the total mass. Individual masses are given as like labeled, and they're small case. So that is our equation, but this is a specific equation for this problem. In general, you can write this equation in the form of summation, because you are adding up x multiplications, right? So this is ith term. So ith term could be starting from 1 all the way to n, and divide by the total mass again. So if you have the first term, then I is equal to 1, it's m1 times x1, plus, because it's a summation, next term becomes m2 times x2, and goes so forth. So in my case, little n is 3 because I have 3 masses. And this is our more general equation. If you have mass distribution, but it is, as you can see, they're like point masses, okay, then we can use this. If they're not point masses and we know the geometry, so if you have like a square or rectangle, let's say, then you can kind of make this kind of a point mass, because you know that this is a nice geometry and the center of mass is gonna be at the center. So you, instead of taking the entire square, you're kind of condensing the mass at the center, geometric center, which happens to be also the center of mass. Okay, as long as the object is homogeneous, so that's important. So these M1, M2, and M3 in my problem could have been something like different shapes. It could be a triangle, circle, and rectangle, but those are the points. They are concentrated at their geometric center, and they happen to be on the same axis. Again, this is a very simple case, and we are solving some problems, but this is kind of how we develop this equation, okay? And actually this equation, last time we did it from the torque, and we don't really understand torque very well. It was very simplified version, but that is going to be very important. So if that wasn't clear, please go back and check the torque how we use torque here. Later on, it's going to get much more complicated, and we also need to add more math, like cross products and such. Okay. So next, I'm going to go to the class file, and there are several multiple choice clicker questions that you need to do. I'm gonna skip this problem because it's like the answer depending on how you choose the points. You can see this I'm talking about this problem here. I'm gonna skip this clicker question because it's not worded very nicely, so and you have slightly different. I think I made it better in your workbook, but I'm gonna skip it anyway. It creates more confusion than helping you. Okay, so next thing is what do we do if we have much more irregular objects like this, like more complex? And what we do is then we need to split up into very small chunks. And you can see that this solid line, it shows the kind of the boundary. So this is our object, right? And we split it up into pieces. And then we can find that each square will have that mass, right? And then you can find the center of mass of that piece. And then you multiply its coordinates again. For the x, it would be mixi. So you can see that it's given here. This, if you're looking at this square, xi is right here, yi is right there. So you have mixi at the top for the center of mass of x, but that's for only one of those. So you have to do all of them. Okay, and then once you do all of them for x-axis and divide by the total mass, you're going to get the center of mass along the x direction. And you're going to do the same thing for y, but there's so many of them. So that kind of is, so if you think about this, yeah, you can approximate that way because the squares are kind of large. They're not small enough. As you can see here, for example, you are overestimating it, right? But if you look at here, you're underestimating it. So it's not going to be perfectly accurate. So what do? We need to make those squares much smaller. And how do we do that? Again, we've been doing this several times. So how do we get from some to much more accurate? It kind of takes us to the calculus, right? So first thing we do is we need to let the edge length of each square go to 0. So it's so small, infinitesimally small, right? And so that we can accurately measure this. And that would mean the mass of each plate will be also very small and equal to differential. So differential dm, okay? And that means d means, again, infinitesimally small mass, okay? Very, very, very small. And that would require, after you do that, then you will have infinite number of squares. Then you are gonna multiply their mass with the dmi's with the xi's and add them up after that, and then divide by total mass. That will give you center of mass after you integrate it, right? So that would mean you need to integrate to get the center of mass. Otherwise, what you're finding is simply differential of center of mass along the x direction. So here I put that earlier equation up here, and this is our new equation. This is for more complex cases, so we will still be using this equation most of the time if it is geometrically possible to find out where the if it's a homogeneous material, and you can find the center of mass easily using its geometry, symmetry. Then we'll be using the first equation. The integrals, I want to explain how we get them, but we usually don't use it in this class. But later on, this is going to be very important. You will use it in next year, depending on your major, but especially MEs will definitely use. I think civils also may need to use. We will do calculations of inertia, and this is where it comes from, and you're going to talk about that. So this kind of is the background to that, okay? So it's important calculations here. So what happened here? So how did we get from this equation to that one? What we did was sum goes to integral, okay? And then you can see that mass becomes dm. So we made that each square mass is very small square, so that mass is very small. And then also xi goes to x because now we are going to integrate it, right? And there's an interval, but it's changing. The integral is over mass, not x, okay? Because your differential is mass, so that's very different. And do not take the integral over x. This integral is done over mass, so that's an important detail. And again, you can do the same thing for the other two dimensions and this similar way. So if you have irregular shapes, very complex objects, this is the way that you can find the center of mass of the object for each axis.